Okay, ladies, we are going to talk about the relationship between linear speed and angular speed, or linear velocity and angular velocity. As you know, velocity is just speed, the way in which something is moving, and we're used to linear speed, miles per hour, meters per second, feet per minute, whatever it is, some unit of distance per unit of time. I'm going to show you on these two circles, and I only have 20 minutes until this preview of the software won't work anymore. But if I show you points E and points F on this circle, when I hit play here, they are going to move at the same linear speed around the circle. Now I tried to make them as equal as I could by eyeballing it, but what I want to show you is I press play, they move around the circle at the same rate, the same linear speed. And that speed right now is whatever this speed is. And I can increase that speed and they move faster around the circle. But what I want you to see is that the angles are changing at the same rate as well. The rate at which the angles are changing up here is called angular speed. Good? Angular velocity. And we can reverse directions. Good. And it's measuring, it's always measuring the angle in the geometry sense. So it's 180 and then it resets back and starts counting down. Good? Okay. Now, the way in which angular speed and linear speed are related is a formula that we already know. We know the formula S equals R theta. Theta is the angle, S is the arc length. Well, if I talk about S and how it relates to t or time, if I divide this side by t, I divide this side by t. Now I have the equation linear speed equals radius times angular speed. Sometimes kids don't like an equation that has this variable down here where you're just solving for s of t. So if you'd like, you could call this linear speed, right? Which we could call v for velocity. And we could say that equals the radius times, and now let's go with, is that a color? No, that's a color. Right here, circle this, call it omega for angular speed. And what it says is the velocity equals the radius times angular speed. The linear speed equals the radius times the angular speed. Now, looking at that formula, I'll write it again here. Linear speed equals the radius times angular speed. If I hit play here, and that equation's going to go away for me to hit play. If I hit play here, yeah, it doesn't want to work. All right. So let's see. Boom. When I unpause it, the linear speeds are the same, so the angular speeds are the same because the two radii are the same length. If I change the radius here, oh, it's not going to let me. There we go. If I change the radius here to make this smaller, okay, now, because the radius is bigger here, if we look back at that equation, all right, what was that equation? That V equals R times angular speed. This is going to stay the same. I have not changed my linear speed. I can't change the linear speed. That's the same here for these 2 points. But the radius just got bigger. So if the radius got bigger, what's going to happen to our angles? Let's see what happens. Let me try to make it more dramatic. Do you see that the angle on the left is now moving faster than the angle on the right? Oh. And if I try to move this back in, hopefully you can see that they're moving at a similar angular velocity. It's hard to tell since they're a little off. Good. If I make this bigger, do you see that one angle is, let me see, I'm going to make this really big so it really slows down. Look at how the angle here is changing very slowly compared to this one. Both particles or both points on the circle are moving at the same linear speed, right? Same linear speed. It's hard to tell that, but they are. They're moving at this speed here, but the angles are changing at much different rates.